This is 1982 AP Physics B. Now this section would be in AP Physics 2 as geometric optics. So in this question they ask that an object is placed at distance of 3/2 of the focal length away from the center of the lens, as is shown in the diagram, and they ask you to calculate the position of the image and trace the ray diagram for locating the image of the object. So let's do that part at first. So again, when I do the ray diagram, I follow certain rules. At first, it's the rays from the object get reflected in all the directions. I'm looking only at 3 specific rays to trace the position of the image. So the first one is going to be parallel to the axis, and then through the focal point of the lens. The second one, and here's the focal point of the lens, and here is another focal point of the lens. For the second ray, it has to go through the focal point and then parallel to the axis, and then the last one goes through the center of the lens, and it's not refracted, it goes straight like that. So the image is going to be formed where the rays meet, and it's going to be somewhere over here. So this is where the image is going to appear, and the image is going to be real, inverted, and looks like it's going to be larger, or it's going to be magnified. My calculations, I would have 1 over the focal length equals to 1 over the distance to the object, which is 3/2 of the focal length. I'm using the lens formula equation, so 1 over the focal length is equal to 1 over dO plus 1 over di. And then here is 1 over di. I'm going to simplify this a little bit. At first, I will times all of them by, actually, let's do this. Times all of them by 2/3, 3/2 of the focal length. So if I times this first one by 3/2 of the focal length, then the letter F, the focal length, is going to cancel from the numerator and denominator. So I will have only 3/2 left. If I times the second fraction by 3/2 of the focal length, then 3/2 of the focal length is going to cancel from the top and the bottom. I'll have 1 left. And then if I times the last fraction by 3/2 of the focal length, I will have 3/2 of the focal length on the top, and di is still at the bottom of the fraction or denominator. Then I'm going to subtract 1 from both sides of the equation. That will give me 1/2. And on the other side, I still have 3/2 of the focal length over di. I'm going to times both sides of the equation by di. So let's just move over here where we have the space. So if I times both sides of the equation by di, I will have di over 2 on one side, and I will have 3/2 of the focal length on the other side. So di is going to be equal to 3 times the focal length. So that's the position where the image can be found. And then for the last part, they say that suppose the object remains fixed and the lens is removed. Another converging lens of focal length f2 is placed in exactly the same position as the first lens. The new real image, larger than the first one, is now formed. Must the focal length of the second lens be greater or less than the focal length of the first one, and justify your answer. So I'm going to calculate the magnification of the first lens. So the magnification of the first lens is going to be negative di over do, and I get negative 3f. That's the one that I just found, the position of DI, and then over DO, and DO is 3/2 of the focal length. So that gives me the magnification is 2. And that is for the first case. And because the position of the object does not change, DI must have increased in the second case when they place the second lens that causes the magnification to be bigger than the one we had in the first case. So DI must have increased. I'm going to look at this equation. 1 over F again equals to 1 over DO plus 1 over DI. And DO in our case did not change. I'm going to find the common denominator for this equation. The common denominator would be F, DO, and DI. I'm going to times every single fraction by this number. So if I times this one by F, DO, DI, I get DO, DI. If I times this fraction by F, DO, DI, I get F, DI. And if I times this fraction by F, DO, DI, I get F, DO. And I'm going to look at what DI depends on. So I have to move my DI to this side and solve for DI. So I'll have DI is equal to FDO divided by, and that is going to be, if I move my FDOI to the other side and factor out, so if I move in this to the other side and factoring out DI, then inside of the parentheses I'm going to have F plus DO. So I will have F plus DO. Because DO did not change, the object is placed in exactly the same position, but DI must have increased in order to give me the larger magnification right here. So this number would get larger, as they say in the second case. Then my focal length must have increased. So the focal length of the second lens must be larger than the focal length of the first lens, the one that they had in the first case. And that's going to be it for FRQ from AP Physics B that was placed on the AP exam in 1982 in geometric optics sections. And thank you so much for watching this video, and I'll see you in the next one.